Hi everyone, my name is Dr. Vanessa Moreno, and in today's video, we're diving into anaerobic conditioning. Quick heads up, I'm a mom of two, so if you hear any little voices in the background, now you know why. All right, let's jump in. So designing an effective training program, understanding physiological demands. Again, this is referring back to our needs analysis. We're just simply expanding on it now. ATP, PCR, examples of this energy system for sports, football, basketball, ice hockey, for instance, as well as some individual sporting events such as track and field, swimming, cycling, gymnastics, specifically the sprinting events. And then you have a combination, essentially a hybrid of aerobic and anaerobic. You have soccer, field hockey, lacrosse, team handball. So these are just sports that have a very specific pattern necessary and a greater reliance on anaerobic activity. For our aerobic, we're going to have other patterns that rely on the aerobic energy system to maintain a prolonged activity rather than short bouts with intermittent recovery. We need to remember our biomechanical patterns, the movements. We do not train muscle, but we are trying to strengthen the movements that are reflected on the field in the weight room, so there is a greater transfer effect from that strength and power back to the field. Of course, we need to discuss the program progression or development. We want to be able to prevent any plateaus, so we don't want our athlete to get stale, if you will. We always want to see some sort of improvement, even if it's little, that's fine. Think of your force velocity curve. The ultimate goal is to move this curve up and to the right. If you're moving it upwards, your athlete is getting stronger. If you're moving it to the right, your athlete is getting faster. If you're doing both, moving it up and to the right, force times velocity is power. And again, as a reminder, your critical training variables: choice, order, frequency, intensity, volume, rest, and then progression. As mentioned on the title page, physiological adaptations are specific to the type of training program employed that the athletes partake in. Therefore, the adaptations commonly generated from anaerobic programs are as follows. We have an increase in transformation of type 2 fibers to more glycolytic subtype, for instance, type 2A or X. There's also a significant elevation in glycolytic enzymes. Phosphofructose kinase, PFK, phosphorylase, lactate dehydrogenase. These enzyme changes lead to an enhanced buffering capacity. Remember, we are only as fast as our weakest link. Enzymes are responsible for breaking something down for further use, for instance, like ATP. ATPase, which is an enzyme utilized to break down ATP for energy to be used for muscle contraction. Therefore, if we have an increase in elevation of these glycolytic enzymes, they may be able to work quicker. You'll be able to recover at a faster rate and improve overall performance as a result of anaerobic conditioning programs. 3, increase in maximum blood lactate concentration. When we have this onset of blood lactate accumulation, you have that burning sensation in your muscle, which then leads to a reduction in your intensity. If we have the ability to increase the threshold of this blood lactate concentration, then we are essentially postponing the onset of fatigue, prolonging activity at a higher level, prolonging potential recovery overall. 4, reduce blood lactate concentration during submaximal exercise. And 5, improve buffering capacity. All in which allows the athlete's ability to maintain high intensity activity or exercise for a longer period of time, for instance, during competitive season, during your games or competition. On the previous slide, it discussed the transformation of muscle fiber subtypes. We have 2 types of muscle fiber for skeletal muscle: fast twitch, known as type 2, and slow twitch, known as type 1. The differences between the slow and the fast are force characteristics, the ability to produce a great amount of force or simply a submaximal amount of force, how quickly we can produce that force, so the velocity, and the fatigue rate, how quickly do our muscles fatigue, or are they fatigue resistant? Slow twitch is exactly as it sounds. It is slow at producing high velocity and high force. But the trade-off is that it has a much higher resistance to fatigue. So in the image to the right, you can see where it says slow and oxidative underneath 1, type 1. These fibers are smaller in size, but have a whole lot of mitochondria. Therefore, they have a lot of ATP ability to maintain exercise for a longer period of time. As we move from slow and oxidative to the right side, we go from type 1 to a continuation of type 1/2A, 2A, and then ultimately 2AX, and finally 2X. So we have type 1, which is very slow, highly oxidative, aerobic, low force production, low velocity contractions, but very resistant to fatigue. On the opposite end, type 2X, think of this as your Superman hero fibers. They are incredibly fast. They are glycolytic and ATP PCR. They're your explosive strength, but able to produce large amounts of force. For this class, we will strictly keep it with 3 different types or subtypes: type 1, type 2A, and type 2X. But note that there is a continuum of muscle for skeletal muscle within the body. It's not simply 1, 2A, 2X. It goes along the spectrum. That, again, the differences are based off of the force characteristics, the contraction speed, as well as the fatigue rate. So again, type 2X, which is fast and glycolytic, ATP, PCR, the trade-off to that is it does not supply us with energy for a long period of time. Therefore, it's very fatigable. How does one person get type 1 or type 2 type of fibers? Well, research has shown that up to 80% it's based off of genetics, where the remainder you might be able to adjust the type of fibers that you may have based off of training. So training might influence the transformation or change in fibers. Research is still unclear. However, typically what is being illustrated at this point in time is that we have a transformation between type 2s, not between type 1 and 2. Therefore, you might have a transformation between a type 2A and type 2X. It highly depends on the type of training stimulus that the program is employing. Metabolic adaptations. As a reminder, there are 3 energy systems that provide fuel for exercise. Anaerobic, so ATP, PCR, as well as the fast glycolysis, the first pathway in glycolysis, less than 30 seconds. The other half of our glycolysis system can also fuel moderate to high intensity activity up to roughly 90 seconds. And anything over that would be more aerobic for prolonged activities at lower intensities. Aerobic versus anaerobic. Anaerobic simply is saying that we are completing activity without oxygen. Now, this does not mean I'm not breathing. It simply means the muscle is working quickly and as hard as it can without oxygen being delivered to the muscle to sustain activity. Where aerobic activity requires the demand for oxygen to be able to supply exercise or supply muscle contraction for exercise for greater than 90 seconds or 2 minutes. This system, again, fuels prolonged activity for low intensity when the demand for oxygen is met with an ability to supply it. How and when are systems activated? All 3 energy systems are always activated regardless of the activity, but the mode of exercise and the intensity of the activity determines which energy system is dominant. So the first 2 energy systems do not require oxygen. And again, this is half of the second system, ATP, PCR, and the first pathway of glycolysis, known as fast glycolysis. Hence, they are termed the anaerobic energy systems. The latter energy system does require oxygen, which is termed aerobic energy systems. So again, there is no single system activation. All 3 are predominant. It just depends on the intensity at which you are at, which will supply the energy for that demand. Right now, if you're sitting listening to this lecture, you're at a low intensity. So your aerobic system is predominantly providing you energy for your brain at this point in time. If you are exercising at a higher intensity, then energy demands will come from our ATP PCR as well as the fast glycolysis system. Drills must reflect the intensity of the movement that stresses the appropriate energy systems. For instance, athletes training in anaerobic sports such as hockey, basketball, or football must use drills that reflect that intensity that they use in their sport. So football, repeated high intensity. They have roughly about 5 seconds per play and roughly 25 seconds of rest between plays. To stress the anaerobic system, high intensity activity should be focused on during workouts. The anaerobic conditioning program should consist of drills and recovery periods that are similar to that of which they complete in the game. They can do this by using the SAID principle, specific adaptation to impose demands. Conditioning programs that focus on specific energy systems cause specific adaptations that result in a more effective utilization of the energy system. They would likely extend the duration of, for instance, sprints or drills for a specific time, dependent on the year, in season, out of season, as well as what energy system they want to focus on. Further, they'll have to take into consideration the training age of the athlete. how to improve the function of the phosphagen system, or ATP PCR. To improve the functioning of the phosphagen energy system, we need to increase the phosphagen concentrations within the muscle by increasing either ATP or creating phosphates. Remember, we have our phosphocreatine, which is the ability to transfer these high energy ATP molecules. We can also enhance the recovery of energy systems between bouts of exercise. However, research findings are not really consistent regarding athletes' ability to cause physiological adaptations to this particular energy system to make it more efficient during training or during a game. Another way would be to supplement, but specifically creatine supplements. It can possibly benefit, but it is difficult to manipulate with training. This should always be secondary or even a third option. Supplementation should never be the primary option in replacement of training. Just like studying, there is no shortcut to studying to understand the material. There is no shortcut to adaptation and training. Supplementation is exactly as what it says. It's a supplement. It should be added to, but not the primary. This is probably the reason why sport supplementation, though, has been so popular over the 15 to 20 years, because it can potentially affect the phosphagen system if and when used appropriately. So, what is the best way to improve the ATP PCR system overall? Research has shown that short duration, 5 to 6 seconds of high intensity exercise, may actually cause only a little bit of change. So they do not appear to cause a change in resting phosphagen system, the ATP or CP mentioned above, or even the enzymes in the system, creatine kinase. During 30 seconds, however, significant elevations in both creatine kinase as well as the myokinase, these are our enzymes, ASE, have been found to improve the ATP PCR system. After roughly 2 to 8 weeks of 3 to 5 days of training specifically for the phosphagen system, there have been significant improvements in ATP or the CP. Differences among studies and athletes are likely related to the training status of the athlete, their experience, durations of sprint times, and length of training program that they've been participating in. But your take-home message, the best way to improve our ATP PCR system is to include 30-second movements at high intensities for between 2 to 8 weeks to enhance our overall ATP and or CP levels. Our second energy system, how to improve the function of glycolytic system. As duration of high intensity exercises increase, the energy required to fuel this exercise is derived primarily from the glycolytic energy system. So again, it's similar to the previous slide. Increasing durations of high intensity exercise, 15 to 30 seconds or even longer, significantly elevate glycolytic enzymes. Our PFK, for instance, our rate limiting enzyme, our weakest link. If we are improving our enzyme function, we improve the efficiency of the glycolytic system. The faster our enzymes works, in theory, the faster our energy systems work. These improvements have been shown to occur within, again, 2 weeks in untrained athletes. Intermittent high-intensity activity with sufficient recovery leads to potentially greater stimulus to glycolytic enzyme adaptation than continuous aerobic work. So if you want to improve our anaerobic system, or the anaerobic portion of the glycolytic system, you should avoid aerobic activity. You should avoid long distance, low intensity, continuous activity. Therefore, you should include intermittent exercise, high intensity interval training, enhancing anaerobic power, but it could also enhance our VO2 max, which is aerobic. So an example of this, 10 sets of 10-second sprints, 1-to-4 ratio, 10 seconds on, 40 seconds off. Fact, aerobic work negatively affects anaerobic, but anaerobic work enhances aerobic work. How to improve the function of the oxidative system. The same stimulus that elevates glycolytic enzyme concentration also appear to significantly increase mitochondrial enzyme activity. These changes enhance the efficiency of the mitochondria. The mitochondria, again, is the powerhouse of energy. It is responsible for supplying fuel during low intensity, sub-maximal exercise. It is responsible, again, for slowing the use of muscle glycogen and reducing lactate production at a given intensity of exercise and delaying the onset of fatigue. It's important implications for anaerobic athletes by helping preserve muscle glycogen and potentially limiting that fatigue rate. Why is it important for the implications of anaerobic athletes? It could possibly lead to an increase in the concentration of the anaerobic enzymes if they're more prevalent when the duration of high intensity exercises exceed 3 minutes. So the implications of enhancing exercise recovery: an increase in oxidative enzymes from anaerobic training programs suggest that these athletes may be able to generate some improvement in their aerobic capacity. Meaning, this may have some important implication for their overall recovery. Our buffering capacity. Its high intensity training results in a lower muscle pH. From exercise physiology, we have an internal environment where we're discussing the pH levels within our body. Our body reflects a normalized pH level, but can change as a result of what we were doing at that moment, whether that's exercise, how we eat, drink, what we drink, how much do we drink. In regards to exercise, when we have a greater buffering capacity, we may reduce muscle pH levels, which would in turn help delay the onset of muscle fatigue. Essentially, that burning sensation forcing athletes to slow down or even cease exercise. Training programs that stress the anaerobic energy system change the ability of the muscle to tolerate these high concentrations of metabolic acidosis. Therefore, this means that it's allowing the muscle to withstand high concentration of this lactic acid buildup. So the buffers that are produced within the muscle, such as bicarbonate and muscle phosphates, help maintain the acid-base balance, this pH level, within the exercising muscle. So, what's my point? This adaptation has an important role in delaying the onset of fatigue during high intensity exercise and in increasing the tolerance of trained athletes to accumulate large concentration of acid due to an improved buffering capacity within the skeletal muscle. An appropriate conditioning program should be based on the needs analysis of the athlete and their specific sport demands. Going back to chapter 1, right? The primary movement patterns, duration of these movements, the number of movements as a whole, and the work to rest ratio are all critical variables that must be identified to prescribe an appropriate exercise. Each sport may be quite different. Even within a single sport, the variability of movements may exist among different positions. So differences in the requirements for each position, for instance, a goalie versus a forward in ice hockey, lineman versus wide receiver in American football, result in varying physiological demands that require different training programs. So with a thorough understanding of the activity demands of the sport, a greater specificity in types of exercises and in the work to rest ratio can be employed to maximize the effectiveness of an overall training program. What is the timing and the duration of a specific anaerobic conditioning program? This is a difficult thing to answer. It is also one of the most frequent asked questions concerning anaerobic conditioning programs is when to begin. This question is not simple to answer, primarily because there is no uniquely correct one. Much of this question is related to the concept of periodized and program implementation, which we will be discussing in greater detail in chapter 11 and 12. That said, nothing in exercise prescription should ever be based on an opinion or just because. Implementation of anaerobic conditioning should be based on scientific evidence and best practices. Specifically, what the sport requires, the athlete requires, the time course of the physiological adaptation. How long does it take for strength adaptation to take place? Conversion to power. If we need hypertrophy. Time reach to peak anaerobic performance. Off-season training. So when considering the time course of the physiological adaptations that occur, they need to calculate the time to begin preparing the athlete to reach their peak performance. They must take this information into consideration when determining the onset of training, proper intensity and volume of training, and manipulation of all of our critical variables. For instance, building off of when and how long and where to start from the previous slide. Matching the work and rest intervals for the sport is important to maximize the effectiveness of an anaerobic training program. Let's take football, for instance. During each game, on average, there are 14.4 offensive series, 4.6 plays per series. Each play has been reported to last an average of 5.49 seconds, ranging from roughly 1.8 to 12.8 in college football. And in between plays, it could be up to 25 seconds of rest. So the conditioning program for football would potentially be based off of the average time per play and rest time between plays allowed for more precise development of a realistic work to rest ratio needed for an anaerobic program. Therefore, the ratio of a 1 to 5 could be used in off-season conditioning. Players could perform short duration sprints that stimulate the movement patterns and range of sprinting distances, volumes, and ratios that reflect a low to high end of realistic work to rest ratios based off of the italicized information above. In comparison to team sports, who perform various types of movements and variable intensities, individual sports may have a different goal depending on that sport. So let's take sprinting, for instance. The goal of a sprinter is to reach peak running velocity as quickly as possible and to maintain that running velocity throughout the length of sprint. Think of Usain Bolt. The ultimate goal for our sprinters is to slow down at the slowest rate, meaning you want to maintain your running velocity for as long as you can. The anaerobic conditioning program for team sport athletes is primarily concerned with preparing them for repeated bouts of high intensity activity with limited rest intervals. In contrast, the sprinters training program is more concerned with the quality of each sprint rather than improving our fatigue rate, since their competition is usually a single race and not repeated bouts. Anaerobic conditioning exercises. There are a number of exercises that can be used as a part of a conditioning program that prepares anaerobic athletes for competition. However, these 6 exercises are the most popular or common ones that we will see. So over the next 6 slides, we'll be discussing each of these individually. The first one, interval sprints. This is an excellent way to improve conditioning for developing anaerobic capacity. So this drill can be performed on a 400-meter track or any measured course that you may have. For instance, a lap equals 400 meters. Typically, the athlete sprints the straightaways and jogs or even walks the curves. Therefore, it's going to result in a 100-meter sprint followed by a 100-meter jog. So the length of the workout and rest period depends on both conditioning and performance. Typically, at the beginning of a program, number and intervals may begin lower or slower between 1 to 2 laps, then progressively increase as the athlete improves. Distance and intensity can vary from short to long intervals, 40 meters or 200 meters. It could also include the curve in the sprint, which now includes a more difficult sprint, as you're including different biomechanical movements as you're running in an angle as opposed to just a single straightaway. Second one, the fartlek training. Typically conducted on a track or a cross-country course, but can be completed pretty much anywhere that you choose, on a sidewalk or a street. The length of the sprint can be altered between short and long distances, with appropriate adjustments made to the rest interval between each sprint. Generally, the same relative work to rest ratio can be maintained for both long and short sprints. So the major difference between the fartlek training and the intervals from the previous slide is that the fartlek runs, the sprints, are of varying lengths. During interval training, the length of the sprint is consistent for the whole workout. Repetition sprints. These are maximal effort sprints for a given distance for X amount of repetitions. So the athlete performs maximal sprints for, again, a given distance that could either be short or long and is associated with a passive rest. Therefore, the athlete stands or sits as they rest until the next bout of sprints. So the work to rest ratio depends on the athlete's conditioning level. 1-to-1 could be to 1-to-4, a 1-to-5, or more or less. So again, this simply depends on the athlete's conditioning level. That said, at the beginning of a program, a 1-to-1 ratio is highly unadvised. Repetition sprints from flying starts. This drill is similar to the repetitive sprints, except that the athlete begins each sprint from a running start, accelerates over 20 meters, and then sprints the required remaining distance. Repetitions and work to rest ratio again depends on the athlete's conditioning level as described in the previous slide. Repetitive relay. This drill uses a group of athletes who perform a relay team. So athletes A sprints to and tags athlete B, who accelerates to athlete C. Then athlete C accelerates to athlete D. This process continues for the length of the track or the distance that is being required. The work to rest ratio is controlled by the number of members of the relay team. For instance, assuming that each member of the relay team is similar in speed, then a group of 5 relay members would result in a 1-to-4 work to rest ratio. Lastly, we have rolling sprints. This drill is performed with at least 4 individuals who are jogging or running at a lower intensity in a line around the track. On the cue of the coach, the last athlete will then sprint to the front of the line. As the athlete reaches the front of the line, on the next signal, the new person who's at the back of the line will sprint to the front and will continue this process until the end of the exercise has been completed. To increase the intensity of the run, reduce the time between signals, or add more runners to the group to increase the distance of the sprint from athlete A to get in front of athlete E. In summary, adaptation to anaerobic training programs include transformation of muscle fiber subtypes, type 1 and type 2, type 2A and X, metabolic adaptations to enzymes, as enzymes allow us to help break down ATP and other resources to sustain activity, as well as buffering capacity, which helps delay the onset of fatigue. Although the number of type 1 and type 2 fibers don't change through training, meaning we don't increase the number of fibers, we just change the adaptation to the fibers that we already have or are born with. Fibers within each category can change to a different subtype, type 2A to type 2X, and vice versa, depending on the training stimulus. This is very specific to the said principle. Most metabolic adaptations to training affect the glycolytic energy system, which provide energy for intense activities lasting less than 3 minutes. In team sports such as football, basketball, ice hockey, or soccer, athletes perform repeated bouts of high-intensity activity with limited rest periods between each bout. Therefore, conditioning should be focused on preparing the athlete for these sport-specific demands, these sport-specific movements. Again, focusing on the movement and the needs of the energy system rather than the muscle utilized. In contrast, individual sports, such as sprinters, focus more on speed endurance in order to experience minimal fatigue towards the later stages of the sprint. Remember, the goal is to slow down at the slowest rate possible in comparison to your competition. One of the primary differences between training programs of these athletes is that sprinters are interested in the quality of each individual sprint, where basketball and football or similar anaerobic sports are primarily focused on the ability to maintain quantity of high intensity activity common to their sport as they have repeated bouts of the same activity for a duration of 3 or so hours. And lastly, an anaerobic conditioning exercise utilizing intervals of intense effort and rest. Therefore, the intervals should be determined by the conditioning level of the athlete as well as the work to rest ratio observed within a realistic sport.